Hi, I'm Rob Bisseling. I'm a full professor in scientific computing at the Mathematics Institute of Utrecht University.
Hi, I'm Thomas Koopman. I'm a PhD student at Radboud University. And in this video, we will talk about the Fourier transform in 3 dimensions and present a parallel algorithm. This was the topic of my master thesis.
You may have seen the one-dimensional Fourier transform already, but let me give you the short definition here. The Fourier transform, the discrete Fourier transform, transforms a vector x of length n into a vector y also of length n. And in this video, we'll start counting at 0 for the vectors that we have. So the definition then of the DFT, the discrete Fourier transform, is that a yk is the sum of a number of terms, and each term is xj e to the power minus 2 pi ijk divided by n. And since we don't want to use all the letters of the alphabet when talking about the formulas, we have introduced a short notation, and the notation would be then that omega n is e to the power minus 2 pi I divided by n, and this helps us in writing the formula as it is to the right of the yk. Also, it is very useful to have an abbreviation for the set of indices 0, 1, 2 up to n minus 1, and this abbreviation will be just n between square brackets, and that gives the formula that you see. We will be talking here about the three-dimensional Fourier transform, and then we get a lot more indices. So the y will then be, the output will be a function of 3 indices, k1, k2, k3, and the input will also have 3 indices, j1, j2, and j3. So here we will get the sum over all the j1s, the j2s, the j3s of this value x in k1, k2, k3 times 3 omega factors, omega n1 to the power j1, k1, and the same for 2 and 3. The total number of points that we have will be just n1 times n2 times n3.
So when parallelizing an algorithm, it is important to think about how we distribute the data. So we will present 3 ways of which we can do this. The first one of which is called the slab distribution. So the slab distribution means we pick one dimension and then distribute over that one. So there are 3 ways we can do this. We can pick the x, y, and z direction, and you can see this in the picture. The colors represent the elements of our cube that are local to one processor. So if we want to do a 3-dimensional FFT of this, and we pick, say, the first cube, then you can see that in the y direction and the z direction, the FFTs are local. However, in the x direction, they are not, so we cannot straightforwardly compute this. That means we need one redistribution to either the second or the third one to make the FFT in the x direction local. If we want to end in the same distribution that we started, for example, if we want to do another FFT, we need one more distribution to get back. We can, at most, have as many processors as we have elements in one direction. So that means that the maximum number of processors we can use is n, or the cubic root of the total number of elements. So if we are not satisfied with the cubic root of the number of elements processors, then we can further refine the slab distribution into a pencil distribution by dividing across one more dimension. So you can see this in the picture, and the elements local to one processor kind of look like a pencil, hence the name. So in contrast to the slab distribution, we cannot do 2 directions locally anymore. If you take the first cube, then you can see that the z direction is local, but the x direction isn't anymore. So we need to do 2 distributions to do all these sequential FFTs. And then if we want to end up in the same distribution as we started, we need one more redistribution. So we have one more than the slab distribution. But the upside of this is that we can further scale the number of processors we can use to the product of 2 dimensions, so the cubic root of n squared. So alternatively, we can also use a cyclic distribution, and this is something we have in any dimension. So starting in 1 dimension, again, the colors represent processors, and you see that we distribute the elements in a round-robin fashion. The first one to the green processor, the second to the yellow, third to blue, fourth to red, and then we start again. We can generalize this to higher dimensions by also splitting up our processor grid in higher dimensions, so either 2 by 2 or 2 by 2 by 2 processors. As you can see, the one-dimensional processors in each direction are not local anymore, so we need to do them in parallel as well. This way, our maximum number of processors we can use is the square root of the number of elements in each direction. So when we take the product, we get the square root of the total amount of processors. The upside of this method is that we only need one redistribution for the parallel algorithm, regardless of the distribution. We start and end in the cyclic distribution.
Okay, let's write down the sequential 1D FFTe algorithm. And then it's based on 4 steps. Step 0, we start with for s equals 0 to p minus 1 do, and we pick out part s of the vector, which is starting at s with a stride of p and a length of n. So the s is the start, p is the stride, and n is the length. And we then pick out xs, xs plus p, xs plus 2p, etc. from this array x of length n. So that's also the notation. And then we perform on this xs, we perform a Fourier transform, and since it has length n over p, we do this.
So we can see this as a transforming a one-dimensional Fourier transform into a two-dimensional Fourier transform. Both the dots and the crosses represent one of these strided subarrays. We can put them under each other and apply an FFT to each one of them.
And that's the FFT of length 4 that we're doing here. Then step 1, we do again a loop, and we multiply all the elements for k equals 0 to n over p minus 1 do xs k becomes omega n to the power s times k xks. And this is called the twiddling. A lovely name.
And even lovelier, we don't have to do anything with the distribution. This can just be done in place.
Step 2 is a transposition. And since these indices, these loops are the same, I just write it within the loop. So y sk is x k s. So we take the x, transform it into a y, and that's the transposition. These two indices, they flip.
We can also represent this as a two-dimensional matrix transpose, as you can see here.
Now, to finish off, we do step 3, the last step. And that is a loop, k equals 0 to n over p minus 1. And we perform an FP, a Fourier transform of length p, on yk that we have here. And that becomes the new yk.
So here we do the rows, do a small FFT of length p.
Okay, and this is the algorithm which is known as the 4-step algorithm. It starts and finishes with a Fourier transform, one of length n over p, one of length p. We will transform this sequential 1D algorithm now into a parallel 1D algorithm. So sequential becomes parallel. And we do not want to write a program for p different programs. We want to write a program for one processor, for processor PS. And this is called the single program multiple data, the SPMD style. So that means that we do not have to write this loop anymore, because this is done, each processor does it for its own data. And the same here for step 1. And this is just done by processor S. And now, since this becomes one big step, we call this a super step. So step 0 and step 1 combined become super step 0. And this is computation. The twiddling just happens as it did before, but just to make some space for the communication, which is extremely important, I move it a little bit up, like this. Just a copy for reasons of space. And then we write here the twiddling, which is just multiplying by the appropriate omega factor. And then we are done with super step 0.
For super step 1, we are going to do the transpose, which is a communication. I will show how it works, and you will either have to trust me or watch the next video to see why this is actually correct. So what we're going to do is that at processor S, we are going to split up our array into p-strided subarrays. So in our notation, that means we have xs, and we have some starting points r, a stride p, and these will have length n over p. And I mean, the R already suggests this. We are going to receive this strided subarray in processor R. So these tried subarrays have length n over p squared because the local part has length n over p and we divide it in p elements. And now what we are going to do is that we are going to squish together this tried subarray and receive it as a contiguous array. So we are going to put this into the receiving processor as XS into the S position. So that it's going to look like S times n over p squared up to S plus 1 times n over p squared minus 1. And that is the first and only communication superstep.
Okay, so we wipe out, of course, the part that was from the sequential program. Gives us also some space. And then what we do is we perform Fourier transforms of length p, and altogether every processor has a part of the array of length n over p. So altogether there are then n over p squared of such small Fourier transforms. So that's why we put a 2 here. Okay, so I'm going to wipe out what we have here. We're going to do n over p squared small FFTs. Let's use a different index, t. So I'm going to do a Fourier transform of length p on my own part of the vector y, because we have, actually we put it and we give it a name, let's call it x. We start at t, then we have a stride of n over p squared, and the length of what we have locally is n over p. So this is the Fourier transform, and we put it in the same place, and let's call it ys of t. This is the start. The stride is n over p squared. And then the total length locally is, as I said, n over p. So this is and that's not step 3, of course. It's not the last step. It's the last super step. We're talking parallel here. So that's super step 2. So what we have here is a parallel 1D algorithm. We will turn this from 1 dimension now into 3 dimensions. So we're going to work on a 3-dimensional array locally. So it's the cyclic distribution. So it's part of the whole array. And we're going to perform a 3-dimensional FFT. We didn't give the notation yet, but what we do is a Fourier transform of length n1 divided by p1 in the first dimension, n divided by 2, n2 divided by p2 in the second dimension, and then also the third dimension. And we execute this on XS, on the local part in the cyclic distribution. So that's what we had here. So we can wipe this out. And then we're going to generalize this loop for k is 0 to n over p. So we can write that as for k equals n over p. That's a new notation, because this is maybe abuse of notation, but it means the set of indices from n1 over p1 times n2 over p2 times n3 over p3. So that is a nice and short notation. And then we can wipe out the one-dimensional version of this. And what we're then going to do is that we multiply x as the kth index. And when we talk about indices, then we're talking about three-dimensional indices, in this case, the kth index, and that's the original xs with k, and then multiplied not by one such omega, but by three such omegas. So it's omega n1 s1 times k1, omega n2, lots of twiddling going on, omega n3 over s3 times. This is the exponent. And I can wipe out then the one-dimensional version.
So the communication step is barely any different in higher dimensions. By this abuse of notation, we do not take a one-dimensional index, but instead, again, a three-dimensional index. So this becomes R in P, which is a three-dimensional index set of P1 times P2 times P3. And then with this notation, we just mean that we take the stride in each dimension, very similar to how we did the cyclic distribution in the higher dimensions. And then again, when we put it in the receiving processor, then this is also a higher dimensional block, so kind of a small subcube. And that's it for the communication step in higher dimensions.
That was an easy job. Now we are generalizing from 1D to 3D the Fourier transform. So what we will be doing is then Fourier transforms of length P1, P2, P3. So this is FP1 times FP2 times FP3 executed on X, the local part, of course. And we just copy what we had here without a 2. And now the 2 should be as a superscript. And I'll tell you what I mean with this a little bit later. So, and this will be then we use a capital Y since it's a multidimensional array, YS. So what we have here, I didn't say that yet, but this is the Kronecker matrix multiplication. It's just a way of saying we're doing a three-dimensional FFT here with P1 in the length in one direction, P2 in the second, and P3 in the third. And this notation, then you have to interpret this as in dimension 1, this is T1 as the starting point, and then N1 divided by P1 squared as the stride. And the local length is, of course, N1 divided by P1. That's the length of the whole local array in that dimension. And then we have something similar for 2 and 3. So you see, notation is very important. So if you abuse the notation well, then the algorithm becomes easy. And then we multiply we do the three-dimensional Fourier transform, and then we get this as output. And that's the parallel 3D fast Fourier transform. We've seen the parallel 3D FFT algorithm, and now we want to analyze the time it takes. And therefore, we use the BSP, the bulk synchronous parallel model, to analyze the time complexity. We have n grid points, which is the total number of points in all elements. On the other hand, we have p processors. The first time gives the time of a perfectly parallelized algorithm, because sequentially we need 5n log n real floating point operations, and this is divided by p. We also have introduced a few extra computations, basically the twiddling that we saw, and those give a time of 12n divided by p, which is of lower order than we had for the first time term. So we do have a little bit of load imbalance. Then we have the communication time. For the communication, we need to redistribute the data once. So in the worst case, all data that are local, n divided by p data, have to move to another processor. So that gives a term of n divided by p times g. But since every element is a complex number consisting of 2 real numbers, we do have a factor of 2 in front of this. Then finally, we have one communication superstep which is being ended by a synchronization, and this costs L. Now in my book, we also have count an L for computation supersteps, but we don't do that here for this particular case.
So let's now talk about some software implementations that are out there for the Fourier transform. All of these need 2 important ingredients. The first one is to take effective use of the processor architecture, which is mostly instruction level parallelism. And the second one is to get the data to the processor fast enough. For the second one, we need to make the program cache friendly. The first package we're talking about is called the Fastest Fourier Transform in the West. And the way this program works is that there are a number of very optimized small FFTs that are generated by the system. And then these are combined in several cache-friendly ways to do a large FFT. It depends on your machine, which algorithm and which codeless is the name for these small FFTs, are the quickest. Therefore, there is some planning done, some runtime measurements on your machine, which is called the FFTW plan. And when this has been computed, you can use this scheme to do as many FFTs as you want. So the fastest Fourier transform in the East is an implementation for the K computer, which uses recursion in order to get a cache-friendly algorithm. It splits up a Fourier transform into smaller and smaller pieces, and eventually they will fit into fast cache memory. The fastest Fourier transform in the South uses the same kind of ideas as FFTW, but instead of including a planning phase, the choosing of codeless and algorithms happens at runtime using runtime specialization. Now, unfortunately, we are not northern enough to claim the fastest Fourier transform in the north. So if anyone wants to fill up this hole, please do. So instead, we had to settle for the fastest Fourier transform in Utrecht, which I also implemented, and you can find that on GitLab. It is done in C, and there are 2 choices for communication library, either MPI or BSP lib. The sequential FFTs in the algorithms are done by FFTW, and the parallelism is achieved by our own code implemented in MPI or BSP lib. The input and output distribution are both cyclic. We have done runtime measurements on the Dutch national supercomputer called Snellius. This is a machine that has 128 cores per node and many nodes, of which we have used up to 32. We compare 4 different libraries, FFTU, which is our cyclic distribution one, PFFT, which uses the pencil distribution, FFTW, which uses the slab distribution, and then we have also compared heFFTe, which also uses the pencil distribution, but we should note that while the first 3 use FFTW for the sequential part, heFFTe uses Intel's MKL. So we cannot compare the last numbers absolutely, only the behavior in scaling. FFTU always starts and ends in the same cyclic distribution. And with PFFT and FFTW, we can let go of this requirement to get some extra speed. We see that when we want to start and end in the same distribution, that FFTU is faster and also more scalable than the slab distribution. If we do not require this, then the runtime measurements are roughly comparable, but PFFT is faster using 32 nodes.
Let us summarize this video. We have developed a parallel 3-dimensional FFT, which has the absolute minimum amount of redistributions, a single all-to-all communication superstep. We can use quite a high number of processors, the square root of n, the number of grid points. And we have implemented this in a package called FFTU, which is available on GitLab. If you want to read more about this, and also about actually we can reach other dimensions than 3, with 5 dimensions or 8 if you want to, then read our paper, which is by Thomas, Koopman, and I. It's called Minimizing Communication in the Multidimensional Fast Fourier Transform